Hey friends, here we are in chapter 13. We're looking at 13.6, circular function. Okay, so I'm going to explain this, and it might not be 100% clear at first, but I think the more we go through the work, the more it will make sense. So let's just hang out and be patient with one another. Please be patient with me. So a circular function, we're going to refer to sine, cosine, and we could even talk about the other trig functions as kind of a circular function, tangent, secant, all that stuff. We can talk about, we're really going to focus on these guys as circular functions because to define all of the, in a sense, you know how functions are. It's some function of y is equal to some function of x. So I can like have sine of x. We're used to sine of theta. So I want you to think of theta as the x value here as all of the domain, I know I'm doing it, I'm talking big stuff, but if we think about the domain of theta, right, or the domain of x, we could have any angle value we want, especially since we saw how we can have angle values that exceed 360 degrees, and we would just keep going around the circle as many times as we want. We can find the sine, cosine, and tangent and all the trig functions of each of those angles. And so let's just talk about sine for a bit. So if I were to look for the sine, let's say, and we did this in another video of an angle that ends in this quadrant, let's say this angle is angle 300 degrees. We know that the reference angle here is going to be 60 degrees. And this is the angle that I would use to determine the sine, cosine, tangent, all the trig values of 300 degrees. So the sine of 300 degrees would be the same as it would be similar to the sine of 60 degrees. So if you guys remember, the sine of 60 degrees is going to be the square root of 3 over 2. But since sine is in this quadrant, since the angle, the terminal ray is in this quadrant, and remember sine is defined as the y value over the r value, we would end up with a negative value because y is negative. I just said a whole lot. Here's what I want you to take home from what we talked about. We'll discuss those things a little bit later. What I want you to take home from that is when I'm dealing with any of these functions, I'm going to continue going around in a circle to get all of the different values for theta and all of the corresponding values for y. It will be based on a circular situation like this. Thus, we will refer to it as a circular function. That's the take home from that particular point. The next point I want to talk about is the idea of a periodic function. So periodic means that the values are going to change, but then they're going to always come back. It's kind of like, and literally this is a periodic function. If we think about the time of day that the sun rises in whatever location you're at, well, particularly, let's say here in North America, if we think about the way the time that the sun rises, it's going to start earlier, then increase, then over time it'll decrease, and then it'll go up. I'm miming this kind of situation here. So this would be a periodic function, a function that kind of repeats over a period of time. So let's take a look at where a periodic or a circular function would be kind of necessary in real life. We're just going to take a glance at this YouTuber visualizing mechanics path through an object rolling without slip. I'll give you the details of the name so we can honor this person's work. Basically, we're looking at over here in the lower left-hand corner, the path of different lights on a tire, in a sense, or on a circular moving object. So we've got red, blue, yellow, purple, and green, and we'll see what the path is like. And so what I want you to observe is that the location, well, just observe it. Let's take a look real quick. So there's the spread of lights. These functions that you see, or the graphs here, actually the red one wouldn't be a function, it would fail in the vertical line test, but the purple one particularly, and the ones that are actual functions, what you would notice here is that there is a repetition, right? It goes over and over again. You see the same values coming up over and over again. So a periodic function, when graphed, will continue over and over again all the time, right? So let me pause here. Let me go back, and I'm going to pause here so I can insert this picture here. Let's see if I can actually break down what a period is next. And so the idea of a period is going to be as follows. So I'm going to do the period in white here. So the period is going to be almost like a segment that I can cut out where we see the beginning, middle, and end, where we end where we started. It's the smallest segment that I could literally capture and kind of cut and paste over and over and over again to make the full function, to make the full graph, okay? So the period is this little section right here. This is one period, and the periodic quality is that it happens over and over again. And functions like sine, cosine, and tangent that are defined on the circular, on the unit circle would be examples of circular functions. I know that's a little vague. Let's get started with a little bit more talk. We'll only do 2 examples today, so it shouldn't be too bad, but we need to spend a little bit of time talking about the unit circle, which is here. And I'm going to kind of go through this rapidly, but I hope that it makes sense. Pause me, slow down if you need a little help. So here we have the X and Y axis. This is a unit circle, meaning that the radius is 1. So the distance from center to edge would be 1, and therefore this point, considering it's the x-axis, would be 1, 0, right? That pretty much makes decent sense. And you know that this angle is 0, and if I want to talk about it in radians, it's still 0. It's 0 radians and 0 degrees. If I move on to this next angle here, this angle represents about 30 degrees. And so I'm going to put 30 degrees here. And if you remember, 30 degrees is pi over 6 in terms of radians, right? And so let me be consistent, do my radians in blue. Pi over 6 will go here. Now the question is, what's the value of this point? You know that this radius is still 1. This value here is still 1. And in a sense, that's the hypotenuse of this triangle where this inner angle is 30 degrees. If you remember the 30, 60, 90 right triangle, you'll remember that the sides were S, 2S, and S root 3. So that means that if this little side is double this side, this has to be 1/2. And this side would be 1/2 root 3. I'm writing, 1/2 times root 3, or root 3 over 2. So what that means in terms of this point here is that this point, and I'm going to write this a little bit larger because it's kind of small, this point would be, anybody willing to take a guess? This point would be root 3 over 2, that's the x value, and the y value would be 1/2. Is that kind of making sense? I'm so hoping so. So this doesn't get too crowded. I've got to erase some of these measurements and keep it moving. This next value is 45 degrees, which we know to be pi over 4. If you don't know this, you might want to copy it down. Pi over 4 is going to, or 45 degrees is going to give me an isosceles right triangle, right? So when I measure the side lengths of this, remembering this is 1, this value here is 1. And I remember that it was S root 2 for the side lengths of an isosceles right triangle. What we have here, if the hypotenuse is 1, then S root 2 is 1. And with a little bit of manipulation, algebraic manipulation, S is equal to root 2 over 2. You know what I did? I rationalized the denominator by multiplying top and bottom by root 2. And therefore, both of these sides would be root 2 over 2 and root 2 over 2. So what's that going to mean for us? That means that our point here is root 2 over 2 and comma root 2 over 2. I'm going to do this whole first quadrant in this way, and then we'll talk about how it relates to the rest of the picture, okay? So now we'll move on to this larger angle, erasing away the things that are unnecessary for us at this time. So this larger angle would be a 60-degree angle, and 60 degrees in radians is pi over 3. All right, so now we're looking at this triangle here. I'm going to highlight it in yellow so you guys can see what I'm talking about. Where this angle is 60, this side is 1. You remember from this last one, right here, this would be 1/2. Let me make it a little bit more clear, this is going to be 1/2, the side opposite the 30 degree, and this side is going to be root 3 over 2. Well, what does that mean for the point that we're looking for? I'm glad you asked. That point would therefore have to be 1/2, that's the x value, and the y value would be root 3 over 2. Finally, we've got an easy one. It's going to be fine, I promise, guys. This is 90 degrees, which we know to be pi over 2 in radians, right? So let me write that down over here. And we know that this point, since the radius is 1, this point has to be 0, 1, has to be 0, 1, because, oh, that's not what I intended. It has to be 0, 1 because we are dealing with this axis. So what does that mean for us? This gives us a whole lot of information about the sine, cosine, tangent, and all the other trig functions in the first quadrant. But after the first quadrant, all of these values will be exactly the same, save their sign. So I'm going to put that information in right now. So instead of writing it, I actually just grabbed it from our textbook and plugged it in here. Notice that the radian measures are not listed. I'm going to scooch this over just a little bit so I can point out a couple things and talk about it. So we have all of these values for the point that the line would pass through if we're going from the center to the edge of the to the center to the edge of the circle. And you remember from last time, we remember that sine of that whatever theta value is going to be y over r. But if r is 1, as in the unit circle, sine of theta is just y in this case, right? Similarly, cosine of theta will be x over r, or x in this case as r is 1, and tangent of theta, and I'll stop there, will be y over x. And that remains because we don't know those values. So we could literally look at this and find the sine, cosine, and tangent, the other trig functions, of any of these angles. When you have these angles, you are expected to know how to, or even coterminal angles that are like these, you're expected to know the sine, cosine, and tangent of it. You need to know that. So one thing that students do is they make a chart. And I for sure think I'm going to need a part 2 for this video. Sorry, Chavalitos, but let's go ahead and do what we can anyway. If we want to find the sine of 0 degrees, we remember that since sine is y, since the coordinate value of y for y here is 0, we're just going to put 0 here. And we can put a 1 for the cosine of theta. And since tangent is 0 over 1, right? Basically sine over cosine. Since that's, we know that tangent is going to be 0. We'll do the same thing for 30 degrees. 30 degrees, the sine value is going to be 1/2 because that's the y value. The cosine value is the x value. Then when I make this a fraction, I get 1 over root 3, which turns out to be root 3 over 3. So I'm going to finish this chart up in that way. Now that my chart for the first quadrant is done, this is really my chart for all of the reference angles. And the only thing I have to remember is what the sign is, positive or negative, not sign like sine curve, but the sign of the value is in each quadrant. We'll discuss that right here. So before we get to that part, what I want you to keep in mind is that in the first quadrant, sine, cosine, tangent, all three of them are going to be positive. But in this quadrant, the cosine, since it takes its value from this x-axis, will actually be negative. And therefore the tangent will be negative, as the tangent can be defined as sine over cosine. So the only thing positive in the second quadrant will be the sine. If we continue thinking like that, the only thing positive in this quadrant will be the tangent, because both sine and cosine are negative. Negative over negative is a positive. And finally over here, the cosine is positive, but the sine, being negative in this quadrant, will be negative. And therefore, the only thing positive here is the cosine. So the way students have remembered it in the past really basically is a mnemonic device. All students take calculus, might be one, ASTC. Use anything you can come up with that might be fun to help you remember. And then we're going to do our little 2 examples in the next video. Thank you guys for riding with me.